Okay, so in this problem, we're going to be using relative effusion rates to find an unknown molar mass. So how a molar mass and rate of effusion are related is through Graham's law of effusion and diffusion that says that the rate of effusion of gas A divided by the rate of effusion of gas B is equal to the square root of the molar mass of gas B divided by the molar mass of gas A. So that's what's going to happen here is we are going to be given all of the variables in here except for one of them, and that one that is missing will be a molar mass, right? And we'll have to solve for that missing molar mass. So it gives us a little bit of info in this opening phrase though that's very important. It says a gas made up of homonuclear diatomic molecules. So what that means is that one of our gases is going to have a formula like this, right? Okay, it's going to be something like O2 or N2 or H2, something like that. It's a gas that's made up of two of the same atoms stuck together, okay? So homonuclear diatomic. So what I'm going to do is I'm going to, assign one of these gases to being that. So I'm going to say that A is my homonuclear diatomic. Okay, so that's going to be my top one there. And it says that this gas escapes through a pinhole 3.16 times as fast as neon gas. So I'm going to let neon be my gas in this case that I kind of like. I can look up the molar mass of that one, can't I, right? So it says write the chemical formula of the gas. So really what I'm going to do is this. I'm going to take the information that's given and then I'm going to solve for the molar mass of my X2, right? And then I'm going to divide that by 2 and that'll tell me what X is. All right, so that's going to be my strategy here. So remember what I said, that A is my 2, so the rate of effusion of my unknown gas over the rate of effusion of a neon is equal to the molar mass of a neon over the molar mass of my unknown gas. There we go. And what's really cool is what we were told is that the rate of effusion of my unknown gas was 3.16 times the rate of effusion of neon. So when I put this term up there in place of this guy, something interesting happened. 3.16 times the rate of effusion of a neon over the rate of effusion of a neon is equal to the molar mass of a neon over the molar mass of my unknown gas. And so the reason why that's interesting is because now that term cancels out and there's only one thing left that we don't know the value of, and that's the molar mass of our unknown gas. So what I've got here is 3.16 is equal to the square root of the molar mass of neon over the molar mass of our unknown gas. So if I square both sides, I can get rid of the square root term, and then if I reorganized, I can see that the molar mass of neon over 3.16 squared is equal to the molar mass of my unknown gas. So the molar mass of neon, I can just look that up in the periodic table. It's 20.18 grams per mole. There we go. So this is going to be 20.18 divided by 3.16 squared. So the molar mass of my unknown gas is 20, turn the calculator on, that always helps, 20.18 divide 3.16 squared. There we go. And it is 2.02 grams per mole. Now, that's not especially helpful what I need to do here is I want to know what the molar mass of X is, because that's something that I'm going to be able to look up in the periodic table. So that's just going to be half of that, isn't it? And so that is 1.01 grams per mole. And you might already have this memorized, but if we now go and find the atom that has molar mass closest to 1.01, there's only one possibility. It's hydrogen. So that means that X is hydrogen and our gas was H2. Okay, so a few little tricks in there. Probably the big one is recognizing how we use the ratio of the rates there, and then also being mindful that the problem was asking about a homonuclear diatomic gas. So once we did get the molar mass of our gas, we had to halve it in order to find the identity of it. Okay, now let's have a look at this one. It says a gas made up of atoms. So really what this is telling you is that we have a monatomic gas. So maybe we have something like helium, or like we saw in the previous example, neon, or argon, something like that. Just something that's just a single atom. So what this means this time is when we solve for the molar mass of our gas, we're going to be able to look up that molar mass directly in the periodic table. We don't have to do anything like halving it or anything like that in order to, before we look it up in the periodic table. So it says a gas made up of atoms escapes through a pinhole 0.155 times as fast as H2 gas. So let's just cut to the chase. So the rate of effusion of our gas over the rate of effusion of hydrogen will be equal to the molar mass of hydrogen over the molar mass of our gas. And we know that the rate of effusion of our gas is 0.155 times the rate of effusion of hydrogen. So we're going to do the same trick again. 0.155 times the rate of effusion of hydrogen over the rate of effusion of hydrogen is equal to the square root of the mass of H2 over the mass of our gas. So these terms here for the rates cancel out, and then that leaves us with the expression that we can go ahead and use to solve for our mass of our unknown. And once we've got that, we just have to look that mass up in the periodic table. So it's going to be, let's write a little neater, 0.155 squared. The mass of H2 is equal to the mass of our unknown, and we already resolved before that this is just 2.002 is the molar mass of H2, isn't it, over 0.155 all squared is equal to our molar mass. And then we'll look that number up directly in the periodic table. So there we are. There's our molar mass of hydrogen already, right? So take that value divided by 0.155 squared equals that. And so our thing is 84.12 grams per mole. We can be a little bit slapdash with our sig figs because we're just looking for the identity. So now I'm going to go to my periodic table and I'm going to look for what is the gas that is nearest to 84.1. And well, here we go. These were my gases are written in red. 84.1. It's got to be krypton, right? There we go. Krypton is the only one that makes any sense. There's nothing that comes near it. These are all my gases, right? With the red labels on them. There's nothing else that makes sense. So it's got to be krypton. So my gas is krypton. Okay. I think that's really it. The only other thing that I could think of is we had a homonuclear diatomic. I don't think we could have a heteronuclear diatomic because then we'd have two atoms in there. So just be aware of like this opening phrase: is the gas made of atoms, or is this gas made of molecules? So just that's a potential kind of like sticking point in this kind of problem that you want to be aware of. Okay, good luck with that. I hope it was helpful.